So as I said, so far we have been doing ANOVA alone, where we are only interested in one parameter or one factor, single factor ANOVA, right. That is why we also call it as one way ANOVA, single factor ANOVA, right. Now we are trying to extend it, okay. See this, as statisticians or as biomedical engineers, these things become important when you conduct experiments. These things will not become important if you are just playing with data, meaning if you are doing data science or data analytics, somebody gave you this data, somebody gave you data, then this becomes slightly irrelevant, okay. Even ANOVA becomes irrelevant, okay. ANOVA may be relevant, yeah, ANOVA will be relevant because even if you get the data, you want to know which treatment is important, which blocking is important, but the moment if you do some data science like machine learning techniques, then logistic regression, that path becomes important. Whereas if you start conducting experiments, then this becomes very relevant, okay. How do I design experiments, right. So the basic statistics that are required for biomedical engineers are the following: one, to conduct experiments, the other one to analyze the outcomes, analyze the data, right. Both of them statistics is required. This part is focused on conducting experiments, whereas the linear regression and logistic regression is mostly for analyzing. Which path do you want to take more? How many of you are interested in conducting experiments and how many of you are interested in analyzing? There is a difference. The methodologies involved are different. When you conduct experiments, I would like to know how do I design the experiments, what are my nuisance factors, what are my controlled, what is my interest, that is what ANOVA, what is my treatment, what is my nuisance, what is confounding. There are many parameters you cannot test it for, so there will be confounding effects, right. The Sensex data give you all information that you can use it directly for your experiment, no, confounding effects will be there, they would have done it for different purpose. So when you conduct experiments, it is a very different ball game, okay. When you analyze, then you start talking about building a model, classifying the outcomes, right. Then you say building a linear model, building a non-linear model, building a neural network or a high-end model. So those are different. Which path do you prefer? Depending upon that, I can tailor under this juncture, I can modify the course at this juncture, because until this point, yes, it is more or less I have covered both. At this juncture, what do you want to do? I can go into machine learning details and then say I can teach you k-means, PCA, all of those dimensionality reduction techniques, clustering techniques, unsupervised, supervised learning techniques. That is one path. The other path is I can get into design of experiments and teach you randomized RCBD, okay, Latin square design, Greco-Latin square, okay, and then I can teach you factorial experiments. So we will try DOE, okay, design of experiments to a certain extent, because those terms you would not have even heard, 2 factorial experiments or k factorial or Latin, Greco-Latin, etc. It is at least good to know that, okay. Then we will, if time permits, we will come back to a few machine learning towards the end. Maybe I will talk about unsupervised and then dimensionality reduction and then LDA possibly, okay. So those are very basics, I will cover them, okay. But for now we will do design of experiments a little more detail, okay. So the next topic what we will learn, what we are going to do is what is called as randomized complete block design, RCBD, okay. We have talked about ANOVA, the natural extension is nothing but called RCBD. Now as I told you, your outcomes may be not just influenced by one factor, it could be influenced by other factor as well, which you want to block. You call it as a nuisance factor. There is a treatment, there is a nuisance, apart from noise. You see what I am saying? When you do an experiment, you have to be very clear now, what is my interest, the factor or factors of interest. The factor of interest, if you take one, then it is typically ANOVA. I have one factor at various levels. So to give you an example, dosage is a factor that I am interested in. Dosage levels is what multiple tau i's are, tau 1 to tau a or that 1 to A is nothing but called as levels. So please understand the jargons, it may be confusing, even if you look at it multiple times you may get confused. So please be very clear, when I say tau, tau is a 1 factor, the levels are 1 to A levels, but still I have only 1 factor of interest. In your case you could have multiple factors of interest or 1 factor of interest, that depends upon your experiment. And I am also talking about a nuisance, which is another factor which will influence your output apart from noise. So noise is something I give it because it is a culmination of various sources. There is now one particular source, various sources contribute to variability in the output. I generally group it and call it as noise. But in your experiment, if you are very sure that one factor is going to give me trouble or influence my output, then categorize it as nuisance, categorize it as nuisance. So to give you an example, in dosage levels, what could be a nuisance? What could be a nuisance? Age group could be a nuisance. I do not want you to test for particular age. Remember, my objective is different. You have to be very clear with the objective. My objective is what? Irrespective of the age group, it should work. Now if I have that, then age group will definitely influence your outcome. The older people are, the lesser effective the drug is, or could be the outcome is more effective, we do not know, right. You will have a significant effect on older group people because they are weak, and then you give this medicine, they become strong, noticeably strong. Whereas for like youth, like your age, taking what is the effect of paracetamol? If I ask you, what will you say? How sensitive are you to paracetamol even? I do not know, right. It is not going to be, you will not report a great change, even if you have to do a subjective change, you will not report a great change unless you are too sick and you are this thing, average you will say, oh okay, nothing happened. Whereas an ibuprofen or any drug which will be like a painkiller, for you it may have a very little effect, for a sports person he will see the impact, or for a person, old age people, they will definitely see the effect of ibuprofen, right. So these are nuisance factors which you want to block, okay. So we have now a model of the form mu plus tau I plus beta j plus epsilon ij. What is beta? Beta is going to be my nuisance factor. So this is my nuisance factor. This is my treatment. And now how is my experiments going to be done? How is my experiments going to be done? How am I going to structure the data? Remember, when I structure the data for ANOVA, it is a matrix. Each row is a treatment, right, each row is a treatment. So levels of treatments from 1 to A levels, tau 1 to tau A. So first row is tau 1, second row experiments are due to tau 2, level 2, level etc. Now when I have to think about blocking, or when I have to think about nuisance, that has also to be included in the matrix. That is also you have to keep in mind during data. That is why I asked who are doing experiments, okay. This is very, very important for those who think about doing experiments, any kinds of experiments. This is a formal way of doing. Does not matter whether you are doing biomedical or sports science, it does not matter. Wherever you collect data, you have to keep this in mind. This is a formal way of, that is why I do not know, statistics for biomedical engineers is not a core, is it a core? No, it is a core, good. It has to be like a core for the entire design of experiments, should be a core for the entire institute basically, because this is a formal way of thinking about experiments, okay. So we said one treatment, one multiple levels, one treatment. Now same, you want to do the same experiment, but there is something nuisance affecting. Let us say I am collecting a simple data, let us say my student has been collecting data for tennis, like collecting data for tennis where I want to track the ball. Lighting condition is something that will affect my results, because the camera has to see the ball. I am collecting data using a camera, right. Lighting condition is a nuisance for me. I know my output will be affected if there is very poor lighting conditions, right. Even you cannot see the ball in the night, how do you expect a camera to see the ball? Not possible, right. So lighting is actually a nuisance, right. I have to avoid the effect of lighting if there is a significant difference to see whether my results are there or not. Simple example, right. Known factor that will influence my output, but I am not interested in lighting influences my output. I know that, I want to block that, I am interested in something else, okay, clear. So known factors typically influence your output and they are nuisance and they want to block it. What is the common sense way of doing it? If you were to do it, what will you do? If you were to do the experiment and you know there is a nuisance, what will you do? So suppose age group is a nuisance, so what will you do? You will choose a particular age group and then do all treatments for that particular age group and move on to another age group, do all treatment levels, move on to another age group, all treatment levels. This is a common sense, so that you are not biased due to age groups. That is what we are going to do. It is a common sense, the way we properly put it in math way. So I am going to have blocks. So let us say there are J blocks, B blocks, sorry, A is treatment, J varying from 1 to B blocks. For each blocking condition or each level of blocking variable, I will conduct all the experiments. So if you want to say lighting conditions as blocking, I will have 3 lighting conditions. Lighting condition in terms of lumens, 200 to 2000 lumens. I will divide it into 4 or 5 and I will perform experiments for each lumen condition and then say, look, my algorithm works for all the lumen conditions of interest of all the conditions, lighting conditions, right. So this is my blocking factor. So now my matrix itself is now arranged into, earlier only rows had meaning, now the columns are having meaning. The columns are nothing but your blocking factors, factor blocking levels of the blocking variable, okay. So you have rows as treatments, columns as blocking levels, rows as treatment levels, columns as blocking levels. So this is how it looks, the table. Once you understand the table, then it becomes very easy, the data structure, the way it is arranged, then it becomes very easy. So you have treatments on the rows, blocks on the columns, and you have the totals, averages can be y1 dot, y dot 1, y dot 2, along the columns it is y dot 1, y dot 2, y dot b, along the rows it is going to be y1 dot, y2 dot up to ya dot, and then you can take the averages. The grand average as usual is y bar dot dot. This is the structure of the RCBD, the way you want to conduct the experiments. One observation for each treatment block. Good. That will simply do what? That is a good point. He is asking a good question, sir. Do I do only one treatment, one for each block and each treatment? Do I do, if you look at 1 comma 1, there is only one data point. Does it even make sense? You don't, if you increase the number of data by experiments, what is going to change? If we, accuracy in terms of what, how? How is the question? So if I increase the number of experiments, suppose I repeat this 10 times, what will change? The structure remains the same. Now instead of having one data point for one entry, you have 10 entries for that. What is going to change? Everybody will say I will have more confidence, accuracy, but what is going to change literally? Degrees of freedom. It affects the degrees of freedom. Capital N minus 1 is the degrees of freedom of a minus 1 divided by n minus a. The degrees of freedom will obviously change. The degrees of freedom will change. It will get multiplied with the number of repetitions. So now you will have, remember the degrees of freedom changes, what will happen? The bounds will tighten for the same confidence interval. Remember it is z alpha by 2 into sigma over root n, right? Z alpha by 2 for that, and I mean if it is normal, if it is t distribution, it is going to be t alpha by 2 comma n minus 1, that degrees of freedom will change. And if degrees of freedom changes, you know the bounds become tighter and tighter. That is what it affects. That is why you need to do repetitions. That is one of the reasons, one of the direct influence of repetitions. I will have more degrees of freedom, that means more bounds, and sigma over root n. This is all we have learned. I do not know why you have to take so much time to think. Sigma over root n, what is the bound itself? I gave you a hint also, confidence, still people did not get it. What is my bound? X bar plus or minus, even if you take normal distribution, it is z alpha by 2 into sigma over root n, that will change, then the bounds will become tighter. So repetitions obviously will help. Okay. So clear, this is the block diagram of RCBD. Now what do we have? Our null hypothesis is the same, treatments, all treatments are equal to 0, at least one treatment not equal to 0, that is my null hypothesis, okay, null and alternate.